Imagine, if you will, taking the mass of every single human being on Earth.
That's about 8 billion of us right now.
Right, all 8 billion. Now, I want you to imagine a force so unfathomably powerful that it could crush all of that human mass down.
Squeezing out literally all the empty space within every single atom.
Exactly. Squeezing and compressing it until every person on this planet fit perfectly inside the space of a single tiny sugar cube.
It's a terrifying image, honestly.
It really is.
But, that is exactly the kind of reality the universe casually engineers every single day.
Yeah, that thought alone completely rewrites my perspective on everything.
Oh, absolutely.
So today we are going to take a deep dive into the darkest, densest, really the most extreme corners of the universe.
The absolute limits of physics.
Right. We are looking at the life cycles and the ultimate, inevitable deaths of stars.
But we're not just going to focus on the violent, chaotic fireworks.
No. I mean, we will definitely get to those massive explosions, but we want to approach this with a sense of immense calm.
I like that. A quiet journey.
Yeah, exactly. We are stepping away from the noise of our daily lives to take a deliberate, soothing journey through the dark, exploring the final endpoints of the cosmos.
I think that is the perfect way to frame it. Because, well, from our vantage point here on Earth, the night sky looks so peaceful.
It's just a silent, glittering tapestry.
Right. Absolute tranquility.
Yeah.
Yet, every single point of light you see up there is a titanic engine. And it's fighting a desperate, losing war.
A war it eventually has to lose.
Exactly. And we're going to explore how those engines work, how they fail, and the bizarre, sometimes totally invisible ghosts they leave behind in the dark.
It's a massive journey. But before we step off the edge of the Earth and into the cosmos, I want to softly break the fourth wall for just a moment.
Go for it.
I want to ask you, yes, you listening to us right now, to please like this video and go subscribe to the incredible channel Decoding the Dark.
They really are phenomenal.
They are. They produce some of the most fascinating, mind-expanding deep dives into the universe, and supporting them directly fuels more journeys exactly like this one.
The work they do to eliminate the unknown is just invaluable. You should definitely subscribe.
Absolutely. So let's map out what we are exploring today. We've got a massive stack of sources.
We do. We're drawing on a vast body of astrophysical research, deep observational data from NASA and ESA.
Right, and some truly mind-bending theoretical physics papers.
Theoretical stuff is where it gets really wild.
It really does. We are going to start with the stable stars we see every night and follow their tracks all the way to theoretical concepts like, well, black dwarfs.
Objects so unimaginably ancient and cold that they don't even exist in our universe yet.
Which is just a crazy concept. But as we navigate this, there's a specific grounding reality to keep in mind, right?
Yes, very much so. I want you, the listener, to hold on to this fact. This is not just abstract physics happening millions of light years away.
It's personal.
It is intimately personal. Everything making up your world right now, the screen you're looking at, the chair supporting you.
The very body.
Exactly. The iron coursing through your blood, the calcium fortifying your bones. Every single heavy atom was forged in the exact brutal processes we're about to calmly unpack.
You are deeply physically connected to the life and death of stars. I just love that.
We are literally talking about our own cosmic ancestry.
We are. So let's start at the very beginning. Because to understand how a star dies, we first have to understand how it manages to survive at all.
Right.
What is a star, fundamentally, when it is in the prime of its life?
Well, the most accurate way to understand a living star is to view it as the site of a perpetual, millions of years long war.
A war between two opposing forces.
Yes, two titanic forces. Astrophysicists refer to the stalemate between these forces as hydrostatic equilibrium.
Hydrostatic equilibrium, I mean, it sounds like a perfectly balanced, peaceful state.
It's balanced, sure, but it is anything but peaceful. On one side of this war, you have gravity.
The ultimate crusher.
Exactly. A star begins as an unfathomably massive cloud of gas, predominantly hydrogen. And gravity is just a relentless inward pulling force.
It just wants to pull everything to the center.
It wants to take all of that mass and crush it inward. It is constantly, endlessly trying to collapse the entire star down to a single infinitely dense point.
So if gravity were the only force operating, the star would just crush itself out of existence instantly.
Instantly, it would be gone.
But it doesn't. Because there is a counteroffensive. Something is pushing back with equal ferocity.
Precisely. As that immense sphere of gas is crushed inward by gravity, the core of the star, the very center, gets incredibly dense.
And unimaginably hot.
Oh, yeah, incredibly hot. We are talking about temperatures exceeding 15 million degrees Celsius.
Wow.
And under those extreme conditions of heat and pressure, atoms of hydrogen are slamming into each other with such intense kinetic energy that they no longer just bounce off one another.
They actually merge.
They fuse. This is nuclear fusion. And the energy released by this process is what pushes outward, fighting back against the crushing weight of gravity.
Okay, I really want to pause and zoom in on that specific fusion process because it's the engine keeping the dark at bay.
It is the heart of the star.
Yeah. For a star like our sun, this is driven by something called the proton chain, or the PEP chain.
Right.
Let's break down exactly how this works because it involves some real quantum strangeness.
It gets very weird very fast.
It does. So at the very center of the star, you have these hydrogen nuclei, which are just solitary protons zipping around at blistering speeds.
Right. And protons, crucially, have a positive electrical charge.
And if you remember basic electromagnetism from grade school, like charges repel each other.
Very strongly. Two positively charged protons actively repel one another. They want to be as far apart as physically possible.
Wait, so if they are actively fighting to stay apart, how does the star ever force them to fuse? I mean, it seems like an impossible barrier.
It is a massive barrier. It's actually known as the Coulomb barrier. And frankly, even at 15 million degrees, classical physics says the protons shouldn't have enough energy to overcome that repulsion.
So the math doesn't work out.
Not with classical physics, no. But quantum mechanics provides a loophole,
Quantum mechanics.
always saving the day. Because subatomic particles don't have exact, rigid locations. They exist in clouds of probability.
Right, the uncertainty principle.
Exactly. So there is a tiny, infinitesimally small chance that a proton can simply tunnel through that repulsive barrier and just, well, appear right next to the other proton.
Just skip the barrier entirely.
Yes. This is called quantum tunneling.
That is wild. The star essentially relies on quantum cheat codes to ignite.
It absolutely does. If quantum tunneling didn't exist, the sun wouldn't shine. None of the stars would.
Wow.
But once they're close enough, the strong nuclear force takes over. It's a force much stronger than electromagnetism, but one that only operates at incredibly short ranges.
And that snaps the two protons together.
It snaps them right together.
But wait, if you snap two protons together, you just have a particle with two positive charges. That's an incredibly unstable isotope of helium. Doesn't that just fall apart immediately?
It usually does. Almost every single time two protons fuse, they instantly break apart again.
So how do we get past that?
Well, occasionally, right at the exact moment they fuse, the weak nuclear force steps in. One of the protons undergoes a sudden transformation.
What kind of transformation?
It sheds its positive electrical charge by emitting a particle called a positron.
Which is the antimatter twin of an electron, right?
Exactly. And having lost its positive charge, the proton becomes a neutral particle, a neutron.
Okay, let me make sure I'm visualizing this correctly. Two protons smash together. One spits out a piece of antimatter to shed its charge and becomes a neutron.
You've got it.
Now you have a proton and a neutron bound together happily. That's an isotope of hydrogen called deuterium.
Spot on. And to balance the fundamental books of physics, specifically something called lepton number conservation.
Right, nature loves to balance the books.
It has to. So the process also has to spit out a ghostly, almost completely massless particle called a neutrino.
Ah, neutrinos, the ultimate cosmic ghosts. They barely interact with normal matter at all, do they?
Hardly at all.
I read in the source material that trillions of neutrinos produced in the core of our sun are passing through your thumbnail every single second, and you don't feel a thing.
That is entirely accurate. A neutrino could travel through a block of solid lead a light year thick and never hit a single atom.
That is just hard to comprehend.
It is. They just instantly ghost out of the star's core and streak across the universe. But the positron, that piece of antimatter, has a very different fate.
Because it's antimatter in a universe made of matter.
Right. Almost immediately it collides with a normal electron in the core. Matter meets antimatter, and they annihilate each other completely.
Just total destruction.
Total annihilation, transforming into pure, high-energy gamma rays.
And there it is, the light.
That's the light.
That gamma ray radiation starts bouncing around, eventually filtering its way up through the layers of the star, losing energy over hundreds of thousands of years.
Bouncing from atom to atom.
Yeah, until it finally leaves the surface as visible light. And the star shines.
And this chain reaction just keeps building. That deuterium captures another proton, to become a light version of helium.
Okay, building up the elements.
Then two of those light heliums smash together to form standard helium-4, spitting two protons back out to keep the whole chain going.
It's an amazing cycle.
It really is. But the profound magic of this entire chaotic dance really comes down to Einstein's famous equation.
E = mc squared.
Energy equals mass times the speed of light squared.
Let's apply that directly to the core of the star. How does that equation explain the outward pressure holding off gravity?
Well, if you were to take a cosmic scale and weigh the 4 original hydrogen protons that started this whole process,
Yeah.
and then you weighed the single helium atom they eventually created at the end,
Yeah.
you would find something strange.
They don't weigh the same.
They don't. The resulting helium atom weighs slightly less than the 4 protons that went into it. About 0.7% of the mass has simply vanished.
And as physics dictates, matter cannot simply vanish. It has to go somewhere.
Exactly. That missing mass was converted entirely into energy.
E = mc squared.
Right. And because c in Einstein's equation is the speed of light, which is a massive number, and you are squaring it.
It gets exponentially larger.
Exactly. Even a microscopic fraction of a gram of mass translates into an apocalyptic amount of energy.
Wow.
Every single second, our sun converts roughly 4 million metric tons of its own mass into pure energy.
4 million tons every second.
Every second, that relentless, unimaginable explosion of energy is what provides the outward pressure that is hydrostatic equilibrium.
I have to ask, though, if a star is fundamentally a gargantuan nuclear fusion bomb converting millions of tons of mass into energy every second,
Yeah.
why doesn't it just detonate? I mean, why doesn't the whole star just blow itself to pieces in one gigantic, instantaneous flash?
It's a brilliant question, and the answer reveals the absolute elegance of hydrostatic equilibrium. It acts as a perfect, self-regulating cosmic thermostat.
A thermostat? Okay, how does that work?
Let's say the fusion rate in the core were to suddenly spike, producing a burst of extra energy.
Okay, so the fire gets hotter.
Right. That extra energy would push outward harder, causing the core of the star to physically expand.
Okay, so the core swells up.
Right. And basic thermodynamics tells us that when a gas expands, it cools down. Its density drops.
Ah, I see.
As the core expands and cools, the protons aren't slamming into each other quite as hard or quite as often, so the fusion rate naturally slows down.
And what if the fusion rate drops too low?
Then the outward pressure weakens. Gravity instantly takes advantage and compresses the core tighter.
Which heats it back up.
Exactly. Compressing a gas heats it up, the density increases, the protons collide more violently, and the fusion rate accelerates back up to normal.
That is just incredibly elegant. It's an exquisitely balanced system.
It really is perfect.
So it's not a chaotic bomb at all. It is much more like a perfectly controlled, slow-burning cosmic campfire.
That's exactly what it is.
As long as the star has hydrogen logs to throw on the fire, the burn remains steady, the pressure remains stable, and the cold, dark grip of gravity is held at bay.
I think the campfire is a perfect analogy. And for stars in the prime of their lives, a phase astronomers call the main sequence.
Right, the main sequence.
This balanced, controlled burn lasts for millions, or even billions, or trillions of years.
You know, that reminds me of how we classify these main sequence stars. Astronomers use a very specific lettering system from our sources called the Morgan-Keenan classification.
Oh yes, O, B, A, F, G, K, and M.
Right. I remember learning this in introductory astronomy with the old mnemonic, oh, be a fine girl, or guy, kiss me.
Oh, classic.
But it always bothered me that the letters are completely out of alphabetical order. Why O, B, A? It feels so arbitrary.
It does feel arbitrary, at least until you look at the history of it. Originally, in the late 1800s, astronomers did classify stars alphabetically from A to Q,
Okay, based on what?
based on the strength of their hydrogen spectral lines. But then, a brilliant astronomer named Annie Jump Cannon,
I know her work. She's part of the group at Harvard.
yes, working with a group of female astronomers at Harvard, often referred to historically as the Harvard computers. She realized the alphabetical system was fundamentally flawed.
How so?
Well, she realized that organizing them by hydrogen lines was confusing, because what really dictated a star's appearance and behavior was its surface temperature.
Oh, not just the hydrogen.
Exactly. So she ruthlessly reorganized the entire system. She dropped a bunch of redundant letters and ordered the remaining ones purely from the hottest stars down to the coolest.
And the astronomical community just went with it.
They adopted her system because it was infinitely more useful, even if it left us with the scrambled letters OBAFGKM.
That is a fantastic piece of history. Annie Jump Cannon basically brought order to the cosmos.
She really did.
So let's walk through her reorganized spectrum.
Sure. On the far left, you have the O-type stars. These are the absolute titans.
The heavyweights.
Incredibly massive, scorching hot, and burning a fierce, brilliant blue-white.
And on the complete opposite end.
On the other end, the M-type stars are the smallest, coolest, dimmest stars, burning a dull red. These are the red dwarfs.
And our sun.
Our sun sits quite comfortably right in the middle as a yellow-white G-type star.
And this brings up a massive, really counterintuitive reality about how long these different stars live.
It usually surprises people.
Because you would naturally assume that a massive, colossal O-type star, which has vastly more hydrogen fuel, like a much bigger gas tank, would live the longest.
Larger tanks should mean a longer road trip.
Exactly.
Yeah.
But if we bring it back to that war of hydrostatic equilibrium, the exact opposite is true. Mass dictates destiny.
Right.
A massive O-type star has an incomprehensible amount of mass, which means it has a horrifying amount of gravity crushing down on its core.
It's immense.
To keep from collapsing under that immense weight, its core has to burn exponentially hotter, denser, and faster to maintain enough outward pressure.
So it burns through its vast reserves of fuel at a furious, totally unsustainable rate.
Precisely. A massive O-type star might burn through its entire hydrogen supply in just a few million years.
Which, on a cosmic scale, is just the blink of an eye.
It lives incredibly fast and dies incredibly young.
Meanwhile, a tiny M-type red dwarf has very little mass. It barely exerts any gravitational pressure on its core at all.
So the red dwarf doesn't need much outward pressure to stay stable.
Right. It doesn't need a massive explosion. It just slowly, quietly sips its hydrogen fuel. The core is churning very slowly.
Just sipping away.
Because of this, a red dwarf can keep its modest little campfire burning for hundreds of billions or even trillions of years.
Trillions.
In fact, the universe is only 13.8 billion years old.
Right.
That means that every single red dwarf ever born in the history of the universe is still alive and shining today.
Wait, really?
Not a single one has ever died.
That is a staggering thought. The universe simply hasn't existed long enough for a red dwarf to run out of fuel. It is the ultimate lesson in cosmic pacing.
It really is.
But let's look at the stars that do run out of fuel. Let's move our focus to the fate of intermediate stars. Stars roughly the size of our sun, between 0.08 and 8 solar masses.
The middle ground.
Eventually, the hydrogen logs run out. What happens to that delicate balance when the fire dies down?
Well, when the core finally exhausts its hydrogen, it is left filled with helium ash.
Because the hydrogen fused into helium.
Exactly. And without hydrogen fusion, the energy production plummets. The outward pressure disappears. Hydrostatic equilibrium is violently broken.
So gravity steps in.
Gravity, which has been patiently pulling inward for billions of years, finally wins the battle. The helium core is no longer supported, so it begins to contract and crush inward under its own massive weight.
But the whole star doesn't just quietly shrink into a dark ball. It reacts in a way that seems entirely backward.
It does.
The core is shrinking, but the star itself expands. How does a shrinking core make a bigger star?
It seems like a paradox, doesn't it?
Yeah, completely counterintuitive.
But as the core contracts under gravity, the immense pressure causes it to heat up dramatically.
Right.
It gets far hotter than it ever was when it was burning hydrogen.
Because of the compression.
Right. And this intense radiating heat from the shrinking helium core warms up the layers of gas immediately surrounding the core. Layers that still contain fresh, unburnt hydrogen.
Oh, so the fire basically moves outward from the center into the surrounding shell.
Exactly. This is called shell burning.
Shell burning, okay.
The hydrogen in this shell ignites, and because it is being heated by the supercompressed core right below it, it burns ferociously.
I imagine that creates a lot of pressure.
An immense amount. This fierce shell fusion generates a massive amount of outward pressure, much more than the star produced during its stable main sequence life.
Wow.
And this fierce new pressure pushes the outer layers of the star violently outward.
So the star's atmosphere balloons out.
It swells enormously, and as those outer layers get pushed further and further away from the hot core, the gas expands and cools down.
Expanding gas cools.
Right. As it cools, its color shifts from yellow-white to a deep glowing red. The star has transformed into a red giant.
It is terrifying to picture our own sun going through this phase.
It will happen.
I know. In about 5 billion years, our sun will become a red giant. It will expand so much that its surface will swallow the orbit of Mercury, then Venus.
And in all likelihood, the Earth as well.
Just imagine standing on a hypothetical surviving planet and just watching a silent, expanding wall of red plasma slowly consuming the entire sky.
An apocalyptic image.
It is, but unfolding with such slow, majestic inevitability.
It is a majestic and terrifying final act, because inside the star is growing increasingly desperate.
What's happening in the core now?
The core continues to shrink and heat up until the temperature reaches a staggering 100 million degrees Celsius.
100 million.
At that extreme temperature, the helium ash itself finally ignites in a sudden, violent event called a helium flash.
So it's burning helium now.
The star is now fusing helium into carbon and sometimes oxygen.
It has found a new fuel source, a new type of log for the fire.
It has. But helium is a terrible, inefficient fuel compared to hydrogen. The star burns through it relatively quickly.
A flash in the pan.
Basically.
Yeah.
And for a star the size of our sun, this is the absolute end of the road.
Why is it the end? Why can't it just keep going and fuse the carbon next?
It all comes back to mass and gravity. Fusing carbon requires temperatures exceeding 500 million degrees.
And a star like our sun just can't do that.
A star with the mass of our sun simply does not have enough gravity to ever crush its core tight enough to generate that kind of heat.
The carbon core is a dead end.
Completely. The fusion engine sputters, and the outward pressure falters for the final time.
Gravity wins for good.
It does. But the death of a star like our sun is not a violent explosion.
Yep.
It is a slow, gentle shedding. The massive, swollen outer layers of the red giant are now so far away from the core that the star's gravity can barely hold on to them.
Because gravity gets weaker over distance.
Exactly. Pushed by thermal pulses from the dying core, these outer layers simply detach and drift away into the cold, silent vacuum of space.
This quiet exhalation creates one of the most breathtaking visual phenomena in the cosmos, doesn't it? A planetary nebula.
Yes. And we should clarify immediately that the name planetary nebula is a complete historical mistake.
It really is.
They have absolutely nothing to do with planets.
Right. I read in the sources that William Herschel, an astronomer back in the 1700s, discovered them through his early telescopes.
You did.
And because they looked like faint, blur, colorful disks, he thought they resembled the newly discovered planet Uranus.
Which is funny in retrospect.
It is. The name stuck, even though it's completely wrong.
Astronomers are notoriously bad at naming things, but visually they are stunning. What you are seeing in a planetary nebula is the ghostly, expanding shell of the star's cast-off atmosphere.
And it glows, right?
It does. As it drifts outward, it is illuminated and ionized by the intense ultraviolet radiation pouring out of the exposed, super-hot core that was left behind.
And they are incredibly diverse, right? They form these delicate shimmering rings, complex hourglass shapes, and massive glowing bubbles of ionized blue, green, and red gas.
Beautiful structure.
But they are a fleeting beauty. They only glow for a brief astronomical moment, maybe tens of thousands of years, before the gas disperses completely into the interstellar medium and just fades from view.
And when that glowing mist finally clears, what remains at the center? The naked, dead core of the star.
A white dwarf.
A white dwarf.
The physical reality of a white dwarf completely breaks my brain.
That breaks all of our brains.
If you look at the raw data for a typical white dwarf, you are looking at an object that contains roughly 0.6 times the mass of our entire sun. That's over 200,000 times the mass of the Earth.
Right.
But all of that mass has been crushed down into a sphere roughly the exact same volume as the Earth.
It requires a complete recalibration of how we understand matter. You are taking the mass of an entire star and packing it into a space the size of a single planet.
The density is incomprehensible.
It really is.
Yeah.
If you were to take a single teaspoon of white dwarf material and bring it to Earth,
Okay, a teaspoon?
that teaspoon would weigh roughly 5 tons.
5 tons.
It would weigh as much as an adult elephant or a large commercial truck sitting in the palm of your hand.
Okay, this brings us to a massive, glaring question.
What's that?
If the fusion engine has completely stopped and there is zero energy pushing outward, why doesn't gravity just keep going? Why doesn't it crush this Earth-sized, super dense diamond down into a speck of dust or a black hole? What could possibly stop the crushing weight of a star if the heat is gone?
This is where classical astrophysics has to hand the reins over to the bizarre world of quantum mechanics.
Quantum mechanics saves the day again.
It really does. The white dwarf avoids total collapse because of a phenomenon known as electron degeneracy pressure.
Electron degeneracy pressure.
To truly understand how this works, we have to look at one of the foundational rules of quantum physics, the Pauli exclusion principle.
Okay, let's unpack this quantum strangeness. How does a subatomic rule hold up an entire star?
Well, in the quantum realm, all particles are divided into two main categories, bosons and fermions.
Bosons and fermions, got it.
Bosons are force carriers, like photons of light. You can cram as many photons as you want into the exact same space.
That's how a laser pointer works, right? Infinite photons occupying the same state.
Exactly. But fermions are the building blocks of matter. Electrons, protons, neutrons. They're all fermions.
And fermions behave differently.
Very differently. The Pauli exclusion principle dictates that no two identical fermions can ever occupy the exact same quantum state simultaneously.
Okay, so they need their own space.
Think of it like a massive theater, where every single seat has a highly specific row, seat number, and assigned ticket.
Okay, I can picture that.
An electron can sit in the seat, but absolutely no other electron is allowed to occupy that exact same seat.
Okay, that makes intuitive sense. Matter takes up space.
Now, let's apply Fermi-Dirac statistics, which is the math that governs these particles, to our collapsing stellar core.
The white dwarf.
Right. Gravity is ruthlessly trying to cram all of these carbon and oxygen atoms into a smaller and smaller space. The pressure is so extreme that the atoms literally shatter.
Just break up.
The electrons are ripped entirely away from their nuclei, creating a chaotic, hyperdense sea of free-floating electrons and naked nuclei.
Gravity is basically tearing the theater down.
It is trying to. Gravity keeps squeezing, trying to force all of these electrons into lower and lower energy states. It's trying to cram everyone into the front row of the theater.
But all the front row seats are taken.
Exactly. The seats fill up completely because the electrons absolutely refuse to violate the Pauli exclusion principle. They refuse to occupy the same quantum state. They push back against being squeezed any closer together.
They just hold the line.
They effectively slam on the brakes and say, there are no empty seats left. You cannot compress us any further.
So it isn't heat holding the star up.
Yeah.
It is the fundamental geometry of quantum mechanics.
Precisely. This quantum resistance, electron degeneracy pressure, is so incredibly powerful that it acts as an unbreakable physical wall.
Wow.
It brings the gravitational collapse of an entire star to a screeching, permanent halt. The white dwarf is held up entirely by the unyielding laws of the unimaginably small.
That is just deeply poetic to me. The rules of the subatomic world are defeating the gravitational might of a star.
It's beautiful physics.
And it wasn't easy for the scientific community to accept this, was it? I mean, there is a fantastic piece of history regarding the discovery of white dwarfs that illustrates just how shocking this was.
You were thinking of Arthur Eddington in Sirius B?
Yes.
It is one of my favorite moments in the history of science.
Mine too. So Sirius is the brightest star in our night sky. But in the 1800s, astronomers noticed it had a tiny wobble, implying there was an invisible companion star orbiting it, tugging on it.
Right, gravity was giving it away.
Eventually, telescope technology improved enough to spot this companion, a tiny speck of light they named Sirius B.
And the mystery deepened in 1914, when the astronomer Walter Adams managed to capture the spectrum of light coming from that tiny speck.
What did he find?
To everyone's shock, the spectrum revealed that the surface of Sirius B was intensely hot, far hotter than our own sun, burning a brilliant white.
Right. So it's incredibly hot, meaning it should be incredibly bright. But it was incredibly dim.
Which is a contradiction.
The only logical conclusion was that the star had to be unimaginably tiny. It had the mass of the sun, but the size of a planet.
Arthur Eddington, one of the greatest astrophysicists of the era, sat down and ran the math to calculate the density required for an object like that to exist.
And what happened?
When he saw the numbers his own equations were spitting out, he suffered extreme cognitive dissonance.
The quote from Eddington is just legendary. He said that the message the star was sending him was, "I am composed of material 3,000 times denser than anything you have ever come across. A ton of my material would be a little nugget that you could put in a matchbox."
And his initial reaction?
A reaction shared by almost all physicists at the time was, "Shut up, don't talk nonsense."
It perfectly encapsulates the crisis in physics at the time. Classical Newtonian physics dictated that such an object was entirely impossible. The pressure should just cause the star to instantly collapse further.
Right, it shouldn't exist.
It took the brand new cutting-edge field of quantum mechanics, developed over the following decade, by minds like Wolfgang Pauli and Enrico Fermi to finally explain how a white dwarf could exist.
It forced us to invent a new kind of physics just to understand what we were looking at.
Exactly.
So the white dwarf just sits there. It is a dead core. No fusion is happening. But it shines brilliantly because it is still searingly hot from the residual heat of its collapsed core.
Just glowing embers.
Which leads us to look into the deep future. What happens when a white dwarf, over unfathomable stretches of time, finally radiates all of that residual heat away into the cold of space?
This brings us to a deeply theoretical, profoundly quiet stage of stellar evolution, the black dwarf.
I love how ominous and mysterious that sounds. A black dwarf, what exactly is it?
A black dwarf is defined as a hypothetical stellar remnant. It is a white dwarf that has cooled down so completely over such an immense stretch of time that it finally reaches thermal equilibrium with the cosmic microwave background radiation.
The cosmic microwave background is basically the ambient temperature of empty space left over from the Big Bang, right?
Correct. It is incredibly cold, about 2.7 Kelvin, which is just a tiny fraction of a degree above absolute zero.
Wow, literally freezing.
When the white dwarf cools to this temperature, it emits absolutely no detectable heat and no visible light. It becomes a frozen, dead, entirely invisible sphere of crystallized carbon and oxygen drifting silently through the pitch black of the cosmos.
But the timescale for this to happen is the real mind-bender here. When you look at the math for how long this cooling process takes, it shatters our perception of time.
It truly does.
Yeah.
The universe, as we understand it, is roughly 13.8 billion years old. To a human mind, that feels like an eternity.
Oh, yeah.
But the amount of time it takes for a single dense white dwarf to radiate away its heat and become a black dwarf is estimated to be somewhere between 10 to the 15th and 10 to the 25th years.
That is a quadrillion years, minimum. Wait, so if you take the entire 13.8 billion year history of the universe, everything that has ever happened from the Big Bang to right now, and multiply it by nearly 100,000 times.
Yes.
That is the wait time for just one white dwarf to finish cooling down.
Precisely. Which leads to a fascinating factual reality.
Yes.
In the 13.8 billion years our universe has existed, there simply hasn't been nearly enough time for a single white dwarf to cool down entirely.
They just haven't had the time.
Therefore, not a single black dwarf exists anywhere in the universe yet. They are ghosts from the end of time.
It is an object that physics demands must eventually exist, but it is locked safely behind a wall of deep time.
Beautifully put.
But theoretical astrophysics doesn't stop there. The research suggests that even this frozen, invisible lump of carbon might have one final, incredibly slow trick up its sleeve.
It might indeed.
I want to talk about the work of theoretical physicist Matt Kaplan and the concept of the black dwarf supernova.
This is where astrophysics crosses over into deep existential philosophy. Kaplan theorized about what happens deep inside the crystalline core of a black dwarf over timescales that make a quadrillion years look like a passing second.
Oh boy.
He asked, what happens in the year 10 to the power of 1100?
A 10 with 1100 zeros after it. I mean, that number is so large it loses all meaning.
It does. Now remember that the black dwarf is physically supported by electron degeneracy pressure. It is structurally stable. And the temperature is essentially absolute zero.
Right, it's frozen solid.
But earlier, we talked about quantum tunneling, how protons in the sun cheat the repulsive barrier to fuse.
Right, the subatomic probability clouds overlapping.
Well, quantum tunneling doesn't require heat. It just requires probability. Normally, the frozen carbon and oxygen nuclei inside a black dwarf don't have anywhere near the energy to fuse. They're locked in a crystal lattice.
So they're just stuck there.
But over a time scale of 10 to the 1100 years, probability takes over. There is an infinitesimally small chance that two carbon nuclei will spontaneously tunnel into each other and fuse.
Almost zero. But given a trillion years, almost zero becomes a mathematical inevitability.
Exactly. This is a profoundly slow process known as pycnonuclear fusion. It is fusion driven entirely by immense density and sheer, incomprehensible amounts of time.
Just slowly ticking away.
Very, very slowly. Atom by atom, century by century, these lighter elements fuse into heavier ones, eventually turning the core into iron.
And as we'll explore shortly, iron is an absolute poison pill for a star. As the black dwarf slowly transforms into a sphere of solid iron, the very electrons that were providing that structural degeneracy pressure begin to be captured by the iron nuclei.
They do. The structural supports begin to rot away. In physics, there's a strict limit on how much mass electron degeneracy pressure can support.
The Chandrasekhar limit.
Right, which is about 1.4 times the mass of the sun. But here's the trick. That limit actually decreases as the chemical composition of the star turns from carbon to iron.
So the ceiling is lowering.
Yes. If the black dwarf started its life with enough mass, say between 1.2 and 1.4 solar masses, this painfully slow picnonuclear fusion will eventually lower the structural limit until it drops below the star's actual physical mass.
The floorboards finally give out.
And when that lowered limit is crossed, gravity, which has been waiting since the dawn of the universe, finally wins the ultimate war.
And what happens?
The frozen black dwarf collapses inward on itself, triggering a sudden catastrophic runaway fusion reaction. It detonates in a massive supernova.
Just imagine the scene. A supernova detonating in a universe that has been dead, frozen, and pitch dark for unfathomable ages. The main sequence stars died out trillions of years ago. The galaxies have long since dissolved into the void. Black holes have evaporated.
It's just endless freezing emptiness.
And then suddenly a single silent explosion of brilliant light.
It is the ultimate final act of the cosmos.
I love the quote from Kaplan regarding his research. When asked why he calculates the math of events no human will ever exist to see, he had this soothing philosophical acceptance.
What did he say?
He said, I became a physicist for one reason. I wanted to think about the big questions. If we can't see them in the sky, then at least we can see them on a computer.
It is a beautiful sentiment. It highlights the profound reach of human curiosity, the desire to mathematically witness the final fireworks of a universe long after our own sun has turned to ash.
I think we all need an atmospheric reset after contemplating a Tumblum scale of 10 to the 1100 years. Just let the sheer vastness of that settle in your mind.
The universe has a patience that is absolute.
It is good to take a breath when navigating these kinds of concepts. The scale can be dizzying.
Absolutely dizzying.
And while we take that brief mental pause, I want to gently remind you that if you are enjoying this quiet, expansive journey through the cosmos, please take a second to like this video and subscribe to Decoding the Dark.
You really won't regret it.
Your direct support is the engine that makes it possible to explore these massive ideas together.
It is a phenomenal community to be a part of.
Okay, let's pivot the narrative. We have spent the first half of this deep dive exploring the drawn-out, almost peaceful deaths of smaller stars.
The gentle exploration into planetary nebulae.
Right. The slow cooling of white dwarfs, the unimaginably long wait for black dwarfs. But the universe has heavier artillery. It is time to look at the spectacular, violently abrupt exits of the universe's heavyweights.
We are moving our focus to stars that are born with roughly 8 times the mass of our sun or more. Their immense gravitational weight forces them onto a completely different, much faster, and much more destructive evolutionary track.
So the war of hydrostatic equilibrium is fought on a totally different scale.
A massively different scale.
Let's walk through the accelerating timetable of fusion in a massive star. It feels like watching a runaway train whose brakes have completely failed.
It's terrifyingly fast.
When a star like our sun runs out of hydrogen, it manages to fuse helium into carbon, and then it simply dies. But a massive star doesn't stop there.
No, its gravity is far too strong. When the helium is depleted and the core collapses, the crush of gravity easily drives the core temperature past the 500 million degrees needed to ignite carbon.
So it just keeps burning.
And it doesn't stop. It fuses carbon into neon. Then it collapses further, heating up to 1 billion degrees to fuse neon into oxygen, then oxygen into silicon.
The star effectively turns into an enormous cosmic onion.
That is the standard and very accurate model. It develops distinct concentric layers.
Like an onion.
Exactly. The outermost shell is still fusing hydrogen. The shell below that is fusing helium, the next carbon, and so on, all the way down to the hypercompressed, scorching hot center.
But the part that is truly terrifying is the velocity of this process. When you look at the timeline for a star that is, say, 20 times the mass of our sun, the acceleration is shocking.
It speeds up drastically.
It burns hydrogen for maybe 10 million years. That is a decent, stable run. Then it switches to helium, which it burns through in roughly 1 million years. But then things get incredibly frantic.
Carbon fusion lasts for a mere 1,000 years.
Wow. From millions to 1,000.
Neon is consumed in a few years. Oxygen fusion lasts for about 1 single year. And the final step, fusing silicon, lasts for barely a week.
A star that lived a stable life for 10 million years suddenly burns through its final reserves of fuel in a matter of days. Why? Why does the timeline compress so violently?
It happens because each successive stage of fusion is drastically less efficient than the last. We have to look at the nuclear binding energy curve.
Okay, the energy payout.
Fusing hydrogen releases a massive bounty of energy. But by the time you are fusing silicon, the energy payout is pitifully small. Yet the immense gravitational weight of the star hasn't changed at all.
So to keep gravity from crushing it, it has to burn fuel faster to make up for the low energy payout.
Exactly. It's like trying to heat a mansion in the winter by burning single sheets of paper instead of massive oak logs. You have to throw paper into the fire at an exhausting, frantic pace just to maintain the temperature.
That sounds exhausting.
And there is a secondary thief involved: neutrino cooling. At these extreme temperatures, the core is producing staggering amounts of neutrinos, which instantly escape the star, carrying massive amounts of thermal energy away into space.
So it's losing heat constantly.
The star is bleeding energy, forcing it to burn fuel even faster just to survive.
And then after a frantic week of burning silicon, the star creates iron in its core. This is the ultimate trap, the iron core. I have to ask, why does the fusion chain suddenly stop at iron? Why is iron the poison pill that kills the star?
This brings us to one of the most profound, inescapable roadblocks in all of nuclear physics. Iron possesses the most tightly bound, stable atomic nucleus in the entire universe.
Okay, so it's very stable.
Very. Up until this precise moment, fusing lighter elements together, hydrogen to helium, carbon to oxygen, resulted in a loss of mass, which released energy, pushing outward. It was an exothermic reaction.
It paid the energy bills.
Yes. But if you take two iron nuclei and try to force them to fuse, the math flips. The resulting nucleus is actually heavier than the two iron nuclei combined.
Wait, heavier, so it doesn't release energy?
It absorbs energy. It is an endothermic reaction.
So instead of throwing logs on the fire to generate heat, the star is suddenly throwing buckets of ice water directly onto the flame.
That is exactly what happens. The precise moment the core accumulates enough iron, the energy production drops to absolute zero.
Boom. The fire goes out.
The outward thermal pressure that has been successfully fighting gravity for 10 million years simply turns off.
Yeah.
Instantly.
Gravity's been patiently waiting for 10 million years.
And gravity's victory is absolute. A core made of solid iron, roughly the size of the Earth but containing more mass than our Sun, goes into a state of catastrophic freefall. It collapses inward on itself at nearly a quarter of the speed of light. The entire implosion takes less than a quarter of a second.
I really want the listener to try and picture the scale of that violence. An Earth-sized sphere of solid iron collapsing inward at 45,000 miles per second, all over in the time it takes to blink.
The collapse is so incomprehensibly violent that the intense pressure actually reverses the process of atomic structure.
Reverses it.
The iron atoms are shattered. The pressure forces the electrons to literally smash into the protons, merging them together to form pure, tightly packed neutrons.
Oh, wow.
In an instant, the entire core transforms into a densely packed, frictionless ball of neutrons.
And this rapid collapse leads directly to the explosion.
Right. The core collapses inward until it hits the absolute physical limit of neutron density. It cannot be compressed a single millimeter further.
A hard stop.
But the rest of the massive star, the outer layers of that onion, are still rushing inward at incredible relativistic speeds. They slam violently into this newly formed, utterly incompressible neutron core and bounce off.
It hits a cosmic brick wall.
It hits the ultimate brick wall. This physical bounce creates a shockwave. And simultaneously, the creation of all those neutrons releases a catastrophic, blinding burst of neutrinos.
But the ghost particles from earlier.
Right. We mentioned earlier that neutrinos usually don't interact with matter. But the density of the collapsing core is so extreme that for a brief fraction of a second, the neutrinos actually get trapped, exerting an immense outward pressure.
So the neutrinos push back.
This combined shock wave rips through the incoming layers of the star, reversing their momentum and blasting them out into space.
The star is ripped apart in a Type II core collapse supernova. It is violence on a scale that defies language. For a few brief weeks, the light from this single exploding star can outshine the combined light of an entire galaxy of 100 billion stars.
It is one of the most energetic events in the universe since the Big Bang.
But before we explore the bizarre remnants left behind by these massive explosions, the research highlights a fascinating, very narrow detour.
Ah, the gap.
Yes. Between the intermediate stars that quietly fade into white dwarfs under 8 solar masses, and the heavyweights that forge iron and explode over 10 solar masses, there is a transitional gap.
The 8 to 10 solar mass range. The in-betweeners.
I love this specific cosmic demographic because for decades, astrophysicists debated heavily about what actually happened to stars in this specific weight class. But the field recently confirmed a third distinct type of supernova.
It was theorized by Kenichi Nomoto back in 1980, but it was only directly observed and verified very recently.
You were talking about the electron capture supernova? It is conceptually a wonderfully elegant mechanism of death?
Very elegant. Let's explain how this mechanism works, because it differs entirely from the iron trap. In these gap stars, the gravity is strong, but the core never quite gets hot enough to fuse all the way down to iron.
So where does it stop?
The fusion chain stalls out at magnesium and neon. So you have a core of magnesium and neon sitting there. It isn't producing energy, but it isn't collapsing either.
What?
Because it is supported by our old friend from the white dwarf phase, electron degeneracy pressure. The electrons are pushing back.
But the gravity of an 8 to 10 solar mass star is intense, far more intense than a white dwarf.
The core is teetering on the absolute brink of collapse. The pressure is so immense that before the star can quietly shed its outer layers and retire as a white dwarf, a bizarre quantum process begins to occur.
What happens?
The magnesium and neon nuclei in the core are squeezed so tightly together with the free electrons that the nuclei begin to physically absorb or capture the electrons.
I think of this like a massive stone building supported by a very specific number of structural steel pillars. The electrons are those steel pillars holding the immense weight of the star up, and suddenly the magnesium and neon just start systematically eating the pillars.
That is an excellent visualization. By capturing the electrons, the star is actively, rapidly destroying the exact quantum pressure that is keeping it alive. The protons in the magnesium and neon nuclei turn into neutrons, and the electron simply vanishes.
The structural support is just gone.
As the electrons disappear, the outward pressure in the core plummets drastically.
The floorboards simply vanish.
And the result is a sudden, simultaneous implosion and explosion. The inner core, having lost its structural support, goes into free fall and collapses down into a dense neutron star, much like the Type II supernova.
And the outer layers.
The gravitational energy released by this sudden core collapse blasts the outer layers of the star away.
It is a supernova triggered not by the sudden failure of a fusion engine, but by the quiet quantum vanishing of the structural floorboards.
It's amazing.
It's brilliant that human beings with our telescopes and computers can finally observe these distant flashes of light and confirm a mathematical theory proposed 40 years ago.
It is a profound testament to how precise our predictive models of the universe have become. We can map the behavior of invisible subatomic particles in the core of a star thousands of light years away.
So, whether a star is destroyed by the iron trap or by capturing its own electrons, these massive stars undergo catastrophic core collapse, which brings us to the extreme remnants left behind in the smoke. Let's look closely at the neutron star.
We talked earlier about the mind-bending density of a white dwarf, the mass of the sun crushed into the size of the Earth. A neutron star takes that absurdity, multiplies it, and pushes it to the absolute breaking point of physical reality.
The numbers for a neutron star are frankly upsetting to think about.
You are dealing with a remnant core that contains roughly 1.4 to 2 times the mass of our entire sun. But during the collapse, the empty space within the atoms themselves was crushed out.
All the space is just gone.
So all of that mass is packed into a perfect sphere just 10 to 20 kilometers across. That is the size of a single city.
A city-sized star.
You could fit a neutron star comfortably within the borders of Manhattan.
The visual of that density is staggering. If you were to take a spoon, scoop up a piece of a neutron star the size of a standard sugar cube, something you could easily hold between your thumb and index finger, and bring it to Earth.
What would it weigh?
That single sugar cube would weigh roughly 1 billion tons.
1 billion tons.
It would weigh as much as every single human being on Earth combined, plus a few thousand mountains.
And the gravitational pull on the surface of that tiny sphere is so unimaginably strong that if you were to drop an object, say a marshmallow, from a height of 1 meter above the surface,
This is soft marshmallow.
it would accelerate so violently that by the time it hit the surface a fraction of a second later, the impact would release the explosive energy of a thermonuclear bomb.
From a marshmallow.
Normal atomic structure simply does not exist here. The crust is an iron lattice, but the interior is a frictionless, superfluid sea of pure neutrons.
And these objects aren't just sitting still in the dark, they're spinning with terrifying speed.
The conservation of angular momentum.
Right. When a giant stellar core, which was already slowly rotating, suddenly collapses down to the size of a city, the conservation of angular momentum takes over. It is exactly like a spinning ice skater pulling their arms tightly into their chest. The rotation accelerates wildly.
And this phenomenon leads us directly to pulsars and magnetars.
When delving into the literature on this, there is a very helpful golden rule to keep the terminology straight. All pulsars are neutron stars, but not all neutron stars are pulsars.
Okay, let's unpack that. What specific mechanics make a neutron star a pulsar?
Yeah, how does that work?
When a massive star collapses into a neutron star, it doesn't just retain its mass and its spin, it also retains its magnetic field. But because that magnetic field has now been squished and compressed down into an area the size of a city, the strength of the field becomes trillions of times stronger than the magnetic field of Earth.
It is a massive magnetic dynamo.
Exactly. And as the neutron star spins, sometimes rotating hundreds of times every single second, this intense magnetic field violently whips around with it.
Whips around, okay.
The field channels charge particles from the surface and blasts incredibly powerful focused beams of electromagnetic radiation out from its magnetic north and south poles.
It acts like the ultimate cosmic lighthouse.
Yes. If the Earth happens to be in the precise path of one of those sweeping beams, our radio telescopes detect a sharp pulse of radio energy every single time the beam sweeps past us.
Pulse, pulse, pulse.
The timing of these pulses is incredibly regular, rivaling the precision of our best atomic clocks.
I always find the history of their discovery fascinating. When Jocelyn Bell Burnell first discovered that regular pulsing signal in 1967, seeing that weird scruff on her chart recorder paper, the signal was so fast and so perfectly timed that they jokingly labeled the anomaly LGM1.
Little green men one.
Yeah.
Because for a brief moment, they genuinely had to consider if they were picking up an artificial beacon from an extraterrestrial civilization.
Yeah.
It seemed too perfectly timed to be natural, but it was just the spinning corpse of a massive star.
And then you have magnetars, which are essentially just neutron stars where the magnetic field is cranked up to 11.
Cranked up to 1,000, really. A magnetar has a magnetic field quadrillions of times stronger than Earth's. It is the most powerful magnetic object in the known universe.
Wow.
If a magnetar were located halfway to the moon, its magnetic field would be strong enough to wipe the data off every credit card on Earth, and it would lethally distort the water molecules in your body from hundreds of thousands of miles away.
It is just sheer hostility to biology.
Pure hostility.
But even neutron stars have their limits, don't they? Just like white dwarfs are constrained by the Chandrasekhar limit, neutron stars have their own ultimate breaking point. Let's delve into the deep physics here. The Tolman-Oppenheimer-Volkoff limit, usually just called the TOV limit.
This limit represents the absolute edge of physics as we currently understand it. Just as electron degeneracy pressure has a breaking point, neutron degeneracy pressure, the quantum rule dictating that neutrons cannot occupy the exact same quantum state, also has a maximum weight limit.
How much mass can a city-sized ball of neutrons actually hold up before even the strong nuclear force and the quantum rules give up?
For many decades, the exact number was heavily debated in astrophysics, primarily because calculating it requires blending quantum mechanics with Einstein's equations of general relativity under conditions of density and gravity that we can never recreate in a laboratory.
Yes, it's too extreme.
Right. However, based on recent data, particularly the observation of gravitational waves from colliding neutron stars, physicists currently estimate the TOV limit sits somewhere around 2.16 solar masses.
Though the models do note that if a neutron star is spinning incredibly fast, the outward centrifugal force might allow it to artificially hold up just a tiny bit more mass, perhaps inflating the limit by 15 to 20%.
That's true.
But the fundamental truth remains. Eventually, there is a hard ceiling. If a remnant core is heavier than that TOV limit, what happens? What comes next?
If the core of a dying star or a collapsing neutron star exceeds the TOV limit, neutron degeneracy pressure completely fails. There is no known structural force left in the universe, quantum or otherwise, to push back against gravity.
Gravity wins.
Gravity wins its final, absolute, and total victory. The mass collapses infinitely inward, shrinking past its own event horizon and tearing a hole in the fabric of space-time. It becomes a black hole.
A point of infinite density, a singularity, the ultimate irreversible endpoint of massive stellar evolution, a region of space-time where the gravitational pull is so unfathomably strong that nothing, not even light, the fastest thing in the universe, can escape its grip. It is the darkest, dark.
It is the final punctuation mark, the ultimate silencing of matter.
Up until this point in our deep dive, we have been looking at stars as lonely, isolated individuals navigating their lives and deaths alone.
Single stars.
Right. But a huge percentage of stars in the universe aren't solitary. They exist in binary systems, locked in a gravitational waltz, orbiting a companion star. What happens when one of these extreme dead remnants has a living neighbor? Let's look at the binary dances.
This is a crucial pivot, because this is exactly where a quiet, dead remnant can suddenly become spectacularly violent all over again. Imagine a typical binary system. One star was slightly more massive, so it lived its life faster, died, and became a dense, Earth-sized white dwarf.
Okay, so we have a white dwarf.
Its companion is a slightly smaller star, perhaps currently entering its red giant phase, swelling up and expanding outward.
So you have this tiny, dead, incredibly dense white dwarf, which has immense surface gravity, and its living companion is swelling up and getting uncomfortably close.
Exactly. If the expanding, loosely held outer atmosphere of the red giant companion crosses a specific gravitational boundary known as the Roche lobe, the intense gravity of the tiny white dwarf will start actively stealing its gas.
It just pulls the gas right off.
The hydrogen gas is physically siphoned off the living companion and begins to spiral down onto the dead white dwarf, forming a swirling, incredibly hot, glowing ring of plasma known as an accretion disk.
The dead star is essentially acting like a cosmic vampire, feeding on the atmosphere of its living companion. But it can't just gorge itself endlessly on this stolen gas without consequences, can it?
It definitely cannot.
This dynamic leads directly to the difference between a nova and a supernova. I always used to get these two terms confused, but the physics separating them are totally different.
It is a vital distinction. Let's start with the smaller event, a nova. As that stolen hydrogen gas continuously piles up on the surface of the white dwarf, it is compressed by the white dwarf's immense gravity and heated to staggering temperatures.
Surface tension building up.
When the pressure and temperature at the very bottom of this stolen hydrogen ocean reach about 10 million degrees, the hydrogen violently ignites.
It triggers a runaway thermonuclear explosion, but crucially, it is happening only on the surface of the star.
Exactly. The surface erupts in a brilliant, blinding flare, a nova that can briefly shine as bright as 100,000 suns. Historically, ancient astronomers would look up at the night sky and see a bright new star appear where there was nothing before, which is exactly where the Latin word nova comes from.
But the key to a nova is survival. The surface explodes, violently blowing the unburnt stolen gas away into space, but the underlying dense carbon-oxygen core of the white dwarf remains entirely intact and undamaged.
It just shakes it off.
And because it is still locked in orbit with its companion, it just patiently starts stealing gas all over again. A nova is a cyclical event. It can repeat every few decades or every few millennia. It is a recurring flash in the dark.
Contrast that cyclical surface flare with a Type Ia supernova. This is a one-time, terminal, catastrophic event.
What pushes the white dwarf past a simple surface flare and into total, absolute destruction.
It happens when the white dwarf is accumulating mass from its companion much faster than it can blow it off through those nova explosions. The white dwarf gets heavier and heavier and heavier. And remember the limit we discussed earlier, the Chandrasekhar limit.
Right, the 1.4 solar masses, the maximum weight that the quantum rule of electron degeneracy pressure can physically support.
Precisely. If the vampire white dwarf greedily steals so much mass that its total weight crosses that exact 1.4 solar mass threshold, the entire star undergoes a sudden catastrophic collapse.
Ooh.
The immense pressure causes the carbon and oxygen deep within the core to simultaneously ignite. A runaway thermonuclear detonation instantly rips the entire white dwarf apart from the inside out. There is no remnant left behind, no core, no black hole. The star is utterly, completely annihilated.
It is erased from the universe. And there is a brilliant consequence to this specific type of death. Because the laws of physics demand that this explosion happens the exact moment the star crosses that precise 1.4 solar mass limit. Every single time, these Type Ii supernovae all explode with roughly the exact same inherent luminosity.
That uniform brightness is one of the most useful tools in modern astrophysics. Astronomers refer to them as standard candles. Because we know the exact true wattage of the explosion based on the mass limit, we can look at how dim the explosion appears to be from Earth and calculate exactly, with incredible precision, how far away that host galaxy is.
These detonating white dwarfs serve as cosmic measuring sticks. We used the violent explosive deaths of these vampire stars to map the scale, the structure, and the accelerating expansion of the entire universe. It is how we discovered dark energy.
It perfectly demonstrates how deeply interconnected every single mechanism in the cosmos truly is. A quantum rule dictates the depth of a star, which allows us to measure the expansion of the universe itself.
Which brings us beautifully to the end of our journey today. We have drifted slowly from the fiery, delicate, quantum-balanced birth of stars through their swelling red old age. We have examined the mind-bending, crushing realities of white dwarfs, the incomprehensible density of neutron stars, the silent finality of black holes, and the eventual, unimaginably distant explosions of black dwarfs.
It is a narrative filled with an immense amount of destruction, countless endings.
It is. But I want to bring this journey back home, gently, to you, the listener, because there is a profound, beautiful symmetry hidden within all of this cosmic destruction. We touched on this at the very beginning, but I want to return to Carl Sagan. He possessed perhaps the most beautiful perspective on this, noting, "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of stardust."
It is an absolute scientific fact. Every single element heavier than helium in the entire universe was forged in the crushing core of a dying star, or synthesized in the ferocious violence of a supernova explosion. The universe creates these massive, brilliant nuclear engines, lets them burn steadily for millions of years, and then violently shatters them, scattering those heavy, complex elements out into the cold nebulas. Over billions of years, those scattered ashes clump together to form rocks, then planets, and eventually, on at least one of those planets, people.
Every single atom around you right now, the device you are holding, the air moving through your lungs, is the cooled ash of these ancient, obliterated cosmic engines. The immense destruction we just spent an hour unpacking was the absolute non-negotiable prerequisite for your existence.
We are, quite literally, a mechanism for the universe to wake up and observe its own beauty.
I would ask you to take this cosmic perspective with you as you step back into your daily life. Carry that stardust with you. And if you appreciated this calm, deep exploration of our universe, please take a moment to like this video and definitively subscribe to Decoding the Dark for more incredible deep dives.
To leave you with a quiet, lingering thought to mull over tonight, we talked about Matt Kaplan's theory of the black dwarf supernova. The mathematical certainty that over quadrillions of years, these invisible frozen stars will slowly fuse their cores into iron and explode.
The final explosions.
Yes. If his calculations hold true, these black dwarf supernovae will be the very final astrophysical events to ever occur in our universe. Long, long after the last main sequence red dwarf is burned out, long after the galaxies have faded to black and the black holes have evaporated, the cosmos will experience a final, solitary fireworks show in total darkness. And then after that very last silent spark fades into the void, there will be absolute, eternal stillness.
What does it mean for our bustling, noisy, light-filled present to know that the universe is inevitably, mathematically marching toward that final, silent spark?
I think it makes the light and the warmth we have right now all the more precious.
It truly does. Take care of yourselves, look up at the night sky a little differently tonight, and we will see you in the next deep dive.